computer. So thanks everyone for coming along, maybe stepping out of the AAS meeting that's ongoing at the moment for this next series of Ringberg talks. So we have two speakers today. The first of which is Eric Liang from the University of Oxford and Tsinghua University, who will be talking to us today about looking for IMF variation with metallicity using Wolf-Rayet galaxies in SDSS MaNGA. So whenever you're ready, Eric, please share your slides and take it away.
Okay, thanks, Tom, for the introduction, and thanks everyone for coming. Let me get it ready. Okay, my name is Eric Liang, or Fuheng Liang. I'm currently a first-year PhD student at the University of Oxford. Although I'm currently working with Professor Martin Bureau on giant molecular clouds, today I'm going to talk about my master's work at Tsinghua University in Beijing. So this work was in collaboration with my previous supervisor, Professor Cheng Li, and some other collaborators. So the title, as you can see here, is we have reviewed metallicity dependence of the stellar initial mass function by using Wolf-Rayet galaxies in the data of Sloan 4 MaNGA survey. So let's get started. So first of all, what are WR galaxies? They are simply defined by their spectral feature of Wolf-Rayet stars. So then what are Wolf-Rayet stars? Right? Wolf-Rayet stars are basically at post-main sequence stage of all stars. So as you can see quite clearly from this table, all stars with initial masses higher than 25 solar masses will go through Wolf-Rayet phases later on after their main sequence and finally explode as a type 2 supernovae. So these kind of stars have very strong stellar winds. The velocity can be up to 2,000 kilometers per second, and this creates very broad emission lines in the winds. This is quite peculiar for stars because usually in stellar spectra, we only see absorption lines. But for Wolf-Rayet stars, or for Wolf-Rayet phases of stars, we can see broad emission lines. This is how we pick them up from the spectrum. And they're also very short-lived because they are very high in mass. And their lifetime is estimated to be mostly lower than 10 mega years. And also because they are few at birth, this makes them a very rare population. So both the WR stars or WR stellar population and the WR galaxy are very rare populations. So on this page, you can see some example spectra of the WR stellar population. On the left, you can see a single fiber example. So this is basically the integrated spectra within this aperture. And on this very beautiful power law continuum, you can see apparently there are two bumps on the stellar continuum. So this is called the blue bump because it's on the blue end, and the other one is called the red bump. So usually the red bump is even more rare than the blue bump. So in the following analysis, we will focus on the blue bump for the search. And this is the zoom in of the two bumps, and they are mainly consist of the helium-2 emission lines or carbon and nitrogen emission lines. And on the right, you can see a different technique. This is the integral field spectroscopy technique from the Khalifa survey. So in this particular WR galaxy, you can see actually more than one WR regions occur. Two of them are extracted here. They both show similarly and significant WR bump feature. So why are we interested in WR galaxies? First, they can be used to study the initial mass function, which I will talk about a little bit more detail on the next page. And then we can also use WR galaxies to study starburst because they are very high mass stars. We believe they can trace very recent starburst activities. And also we can use them to study stellar evolution models, which we will also use in this project. And also they are believed to have some link with some special supernovae events or some gamma ray bursts because they are high mass stars. They are believed to be possibly the progenitors of those. And we can also study the feedback of high mass stars to the ISM because, as I said, they have very strong stellar winds. That means they must have a very strong influence on the ISM. And also, we actually observe some coexistence of WR stellar population with AGN. So we can also study AGN influence on star formation. So this is the initial mass function. I believe many of you are very familiar with this initial mass function already. let me briefly remind you. It's basically describing how many stars you will have in each different mass beam at birth. And this form is a simple power law form proposed by Sir Peter like 70 years ago. And then different forms and different parameters have been proposed. You can see on this figure. And we are trying to constrain the high mass end of this initial mass function because WR population or WR galaxies have living high mass stars. So it is quite straightforward for us to constrain the high mass end. And also we have a question is whether this initial mass function vary from environments to environments, because previously when people first proposed this, the form of this function, it was based on counts of stars in the solar neighborhood, or at most in the Milky Way. So it's natural that we are curious whether this function is the same in external galaxies, also even to high redshift at very early epoch of the universe. So this is a very important question. And the initial mass function is also very fundamental in the stellar population synthesis. So this is quite a fundamental building block of our techniques and also of our understanding of galaxy evolution. So let's move on to the data and identification part. This is a brief overview of the MaNGA survey. It targets at a very large sample, 10,000 galaxies in the nearby universe. And it's a 2D spatially, it's actually a 3D. It offers spatially resolved spectroscopy. And as you can see, the central spectra extracted here looks quite different from the outskirts of the galaxy. In the outskirts, we can still see emission lines, which trace the young stellar population. In the center part, we can only see very strong absorption lines and the D4000 break, which is relatively old. So this is also the initial motivation of this project, because previously we only had Sloan single fiber data of nearby galaxies. So we can only trace the central starburst and central WR features. Now with MaNGA data, we have a wider field of view coverage, and we also have the spatial resolution for us to detect more starburst and WR features on the outskirts of galaxies. So this is our procedures in the search or in the catalog construction. We first find H2 regions by H-alpha surface brightness threshold. The reason we are doing this step is to try to raise the signal-to-noise ratio of the spectrum. And you can see here, these are the identified H2 regions in this example galaxy. And then we stack spectra within each H2 region. So in this step, we raise the signal-to-noise ratio. We raise the spectrum quality. So after this step, we have about 8,000 H2 regions corresponding to 8,000 stacked spectra. And then we perform the full spectrum fitting to those 8,000 spectra with Miller's templates. And finally, we do a visual inspection of those several thousand spectra to finalize our catalog. So our catalog consists of 267 H2 regions, which have WR feature, and they are distributed in 90 galaxies, which we call WR galaxies. And this was based on the half of the entire MaNGA sample available at that time. And this is already published in a paper in 2020. So on this page, I'm showing some basic properties of our catalog. Here, I'm actually combining our new catalog with two previous Sloan catalogs to enlarge our sample size. And also, different catalogs actually have different bias from their different empirical searches. So this combination can help us to cover a wider parameter space as well as to alleviate the bias of empirical searches. So on the left, you can see the color mass diagram. So basically, our new catalog is in this empty blue circle. It occupies the high mass end of the blue cloud of galaxies, while the two other Sloan sample are distributed more in the bluer region of this diagram. And on the right, you can see the star-forming main sequence here in the background. And our new catalog occupies slightly higher than the star-forming main sequence, while the two Sloan catalogs are even higher in star formation rate at any given stellar mass. So basically, that's how the basic parameters are distributed for our catalog and the 2 previous catalogs. And we also had a look at the metallicity of our resolved WR regions. So plotted in gray, this is the general population of galaxies on the mass metallicity relation. And our new catalog is plotted in the blue dots. So apparently they are lower than the general trend. So this is how we say that our WR regions tend to be metal poor. And this is already a hint that we can find more WR regions in the metal poor environments than in the general metallicity environments. This might provide a hint for the initial mass function, where we can see more WR regions or more high mass stars in the low metallicity environments, which means flatter IMF at low metallicity. But this is just a very qualitative analysis, and we will move on to some quantitative analysis later. Okay, how do we precisely use our WR observation to constrain the initial mass function? First, we introduce some stellar evolutionary models. One of them is the Starburst99 model, which is a classic one, but it only has single star evolution. And we also use BPASS evolutionary models. It has both single and binary evolution tracks. And both of these models provides many different model templates with different combinations of IMFs and stellar metallicities. And of course, we have a lot of different snapshots of them, which are basically the ages of the stellar templates. So we also use this software to analyze our observed spectrum. We use this Bayesian inference code to basically derive the stellar metallicity from a spectral fitting for our observed WR population. With this tailored star formation history of a recent burst superposed on old exponential decay. So we can precisely extract the metallicity of our WR stellar population. And then our first approach to do the comparison is to measure the WR features. This is basically the equivalent width. We measure the equivalent width for both observed spectra and model spectra, and then we compare them quite straightforwardly in different metallicity beams. And the second approach is to fit the WR spectra directly with model spectra as templates. And as I said, the model spectra actually has many different combinations of IMFs and stellar metallicities. In this sense, we actually, for each WR spectrum, we carried out multiple fittings. And among those fittings, we can pick the fitting with the highest Bayesian evidence. This means that fitting for this spectrum is optimal. And then we can see which IMF slope was used as the input parameter for that particular fitting. So in this way, we can extract the optimal IMF slope for each observed WR spectrum. And then we have a sample, and then we can do some correlations. So first, let's compare some of the parameters. So this is comparing with Starburst99 model. So it's single stellar evolutionary model. And different lines are the model predictions on this 2D parameter space. And all the dots and the crosses are from the observational sample. So this is comparing the equivalent width of the WR feature versus the equivalent width of the H beta. And on the second row is the flux of the WR feature normalized by the flux of H beta line. So you can see the model lines are performing like the evolutionary tracks on this parameter space. And from left to right, we are having increasing metallicity grids. And on the left-hand side, you can see at the lowest metallicity, it seems our data are mostly outside the red line. The red line is the alpha equal to 1 slope. This is the flattest slope. And on the right-hand side, you can see our data points kind of migrated into the inner region of the blue line. So the blue line is the steepest slope. This means at the lower metallicity range, it seems our data agrees better with the flatter IMF. And at the highest metallicity range, it seems our data agrees better with the steepest IMF. So another parameter comparison is using the BPASS model. So again, the lines are from the models, but different from the previous slide, this is showing the BPASS model from alpha equal to 2 to alpha equal to 2.7. So basically, if we trace any fixed IMF input, we can see an increase of the predicted WR feature with metallicity. However, in our data points, we do not see any increase with metallicity. So this increase in the model, in the theoretical model, is due to the stellar winds. The mass loss rate has a dependence on metallicity. However, we do not see that trend in observed data. So this means we must need different IMFs at different metallicities to explain our data. So in more detail, you can see the data at low metallicity seems to agree slightly better with this blue line, which is the flatter line. And at the high metallicity, our data seems to agree better with the green line. So this is the steepest line. And this is also true for the binary evolution comparison. Although it's slightly less obvious at the low metallicity end, but this trend is generally similar to this panel, where we have the data points agree slightly better with the green line at the higher metallicity end. Okay, now let's move on to the second approach. Let me briefly repeat the procedure used. So we directly fit our spectra with all IMF templates with different combinations of IMF inputs. And then for each spectrum, among those different fittings, we can extract a best fit based on Bayesian evidence. So we can know the best fit IMF slope for each spectrum. And then we group the spectra by their optimal IMF slopes. As you can see, we group them into 3 subgroups. And then finally, we plot the cumulative distribution of their metallicity. So you can see the green line represents the steepest IMF of 2.7. And it seems in the central region here, the steepest IMF tends to rise later in the metallicity domain. This means it slightly favors the higher metallicity compared to the blue and orange line. And this is also true in the binary case. The green line of 2.7 IMF slope rises at higher metallicity. So this also reveals a potential trend in this correlation. So how do we understand this from simulations? This is a simulation work published in 2010. And these 4 panels are showing the temperature. And on the right, you can see the density. So the temperature, on the temperature panels, you can also see the Jeans length indicated by the circles on the bottom left. So you can see in the lowest metallicity simulation, the Jeans length is the largest given this temperature. So this is also consistent with creating more high mass stars. And also for the on the density plot, if we focus on this panel, you can also see at the lowest metallicity regime here, you can see there are not many obvious cores compared with this one. So in this one, you can see many cores fragmented from the large molecular cloud. So this is at higher metallicity. So this means at higher metallicity, it might produce more low mass stars, while in the low metallicity, it might produce some fewer but bigger high mass stars. Okay, I will move on to the final page. So basically, the initial mass function is a key ingredient for understanding galaxy evolution. And since Wolf-Rayet galaxies have very significant feature of living high mass stars, they are ideal for constraining the initial mass function at the high mass end. There are some recent literature also trying to constrain the initial mass function, but I think the Wolf-Rayet galaxies are among the very few approaches that are most sensitive to the high mass end. While some other approaches are sensitive to the low mass end, some other approaches are sensitive to the entire spectrum of the entire IMF. And we have identified 90 WR galaxies from MaNGA survey, and they tend to be metal poor, implying more massive stars at low Z. And we also did some preciser comparison with the 2 approaches, which is comparing WR parameters and also full spectrum fitting. So both of these 2 approaches reveal that the flatter IMF or top-heavy IMF is preferred at low metallicity end. And this trend exists for both singular models and binary models. And this is also the first time in literature, as far as I know, that binary models is explicitly discussed in this kind of studies. So that's all for my talk. Thank you for your attention, and I'm welcoming your comments and questions.
Great. Thank you. So if people would like to ask questions, they can use the raise hand emoji. I see there's already a question from Alberto.
Hey, thank you. So I'm just curious, how do you square this claim for a systematic change in the IMF at lower metallicities with the measurements from the local group, where you can do direct measurements of IMF at lower metallicities, and you don't, well, I mean, these measurements are difficult, but it's not a clear trend or a clear line of evidence showing a change.
Sorry, did you say the local universe, or sorry, I didn't quite get the question. Sorry.
Yeah, I'm talking about the measurements, particularly in the local group, where you can do the counting of the individual stars, etc., and try to determine an IMF. So how do you square this difference between your results and what people tend to get in the local group, which is not an obvious systematic technique?
Okay, so by saying local universe, you mean the very nearby galaxies, where people tend to think the initial mass function tend to be a universal one, right?
I'm talking about the local group, where you get down to metallicities of 1/5 solar.
Yeah, I see. Actually, to be honest, I'm not familiar enough with the literature done in the local group. So it seems I'm not in the best position to answer this question. But I would say within the local group, we might be slightly constrained with the environments we have. It seems in the local group, we do not trace galaxies in all possible environments, for example, metallicity or stellar velocity dispersion. We just do not see we just do not see many different types of galaxies if we are constrained to the local group. So I think in the local group, we can measure things more precisely. We can get more accurate measurements of both the initial mass function as well as the metallicity. But it seems to me that if we can go beyond the local group, then although our measurements of metallicity will be harder and more challenging and more affected by the systematic noise, but our environments of galaxies will be more complete compared to the entire galaxy population. That's my understanding. But really, I'm not in the best position to compare our results directly with the results from the local group. So yeah, if I have a chance, I will check the literature and then respond to you by email, if that's okay.
Wait, no, I mean, the systematics of the two measurements are different, no? Because here you're trying to do a spectral measurement. So I'm a bit worried about that. But sorry, I missed the very beginning of your talk, and I apologize. What is a 4615 angstrom feature precisely that you were using?
Here, that's basically the equivalent width of the blue bump.
The blue bump. Okay, great.
That's at, yeah.
Thank you.
I think we've got time for one more question. So I saw Guillermo's hand up, but if you want to ask your question in the chat, Eva, and maybe Eric can respond to it in there, but I think we'll need to move on to the next talk after this question.
Hi, Eric. Thanks for a very nice talk. Can you go back to the plot where you compare with the BPASS models, that one? So the plot on the right, it would seem to me like, you know, it would seem to me like the orange line is pretty close to going through most of your points. And in a way, I think the fundamental question here is, you know, is metallicity really affecting the IMF, or is metallicity affecting the evolutionary models or the way these high mass stars evolve, and whether they go through a Wolf-Rayet phase and for how long and how often, etc. Right? And what the BPASS models are telling you basically is that binarity has a big effect on this, right? That's why the plot on the left and the plot on the right look different, right? I mean, you can basically produce this, you know, strong Wolf-Rayet signals by, you know, binary stellar evolution. So my question is, you know, what are the levels of systematic uncertainty in these binary evolutionary models? And are they within a scale or a range where you maybe can easily explain your data by allowing a single IMF and allowing the uncertainty, the systematic uncertainty of how binary populations evolve, move within a reasonable range? You know what I mean?
Yeah, I see. Yeah. So first of all, I would say our evidence is slightly weaker if we look at the binary evolution compared with the single evolution, as I mentioned. So this is also a very important lesson for us we have to consider the binary evolution if we are going to make this study preciser and more accurate. And second, I agree with you that the orange line seems to agree with our data pretty well, except some slight deviation here on the high mass end, on the high metallicity end. But I would still argue we can see this dramatic increase in each of the model prediction. However, we do not see any dramatic increase in our observed WR feature. So this might give us a hint or a preliminary evidence that we need IMF variation to explain all the data. And to make this argument more quantitative, I think you are right. The systematic error is very important if we are gonna say this is a very strong evidence, or rather this is only a preliminary evidence. But unfortunately, I do not know how much, for example, how many dexes the prediction of the binary evolution has, because as far as I know, the high mass star evolution is, among others, is one of the most tricky parts of the stellar evolutionary models. So we are still looking forward to later release of BPASS or later release of other stellar population models to help us make this comparison more accurate and preciser. Yeah, that's basically that much I know at current data quality. So you can also see that our data points have very large scatter and variance in the background. So this is quite a preliminary attempt to use WR galaxies in this way, I think. Yeah,
Thank you very much.
Yeah, you also mentioned the evolutionary models effect on the, the effect of metallicity on many different things. You mentioned the stellar winds, the evolution of stars. I think that is already taken care of by the evolutionary models. So the evolutionary models are already considering the mass loss rate as a function of metallicity. So we are safe just to compare their predicted results.
Yeah, I mean, they consider that. They consider them, right? But they do have some level of uncertainty, right? Yeah. I mean, that's why on the left plot you have this very steep rise, right? That's because it's harder to produce these winds in low metallicity environments because you don't have any metals against you can push, right, the wind. Right. But then binaries help you a lot because of they remove the outer layers of the stars, et cetera, et cetera. So yeah, I mean, I guess all I'm saying is when I look at this plot, what I see is that assuming the models are perfect, you are like within 1.5 to 2 sigma of a constant saltpeter IMF as a function of metallicity in the plot on the right? So and I would imagine that once you fold in the level of uncertainty that we have, especially on high mass stellar evolution, that this data would be fairly consistent with a constant IMF as a function of metallicity, close to saltpeter. So yeah, I think looking into the the way these models evolve and how uncertain they are, of course, is a big area. But it's very important to your work. Yeah. So
yeah, that's
thanks a lot.
Important. Yeah, I agree. Thank you for your comment. And sorry, I'm not doing very well on time, and I think I should stop here.
It's okay. Thanks again, Eric. So yeah, we'll move on now, but there are some questions in the chat if you want to respond to them there. So our second speaker is Lachlan Lancaster from Princeton University. Who'll be talking to us today about a fractal model for turbulent stellar wind bubbles. So whenever you're ready, please, Lachlan, take it away.
Can everyone hear me and see my slides?
Yep.
Okay, so hi everyone. Thanks for having me. As Tom mentioned, I'm going to be talking about turbulent stellar winds. This is some work recently out with my collaborators, my advisor Eve Ostreicher, and collaborators Junggu Kim and Chenggu Kim, also all at Minsk. So it was very nice also to get this sort of intro to thinking about the motivations behind stellar winds from Eric, and talking about Wolf-Rayet stars and their feedback. I'm mostly thinking about sort of the things that happened before Wolf-Rayet stars, and that's mostly O and B stars, some massive stellar winds from O and B stars. Hopefully you can't hear the landscapers outside of my apartment, but please, I apologize for any noise. So anyway, the motivations here, I'll go over this quickly, but basically star formation is a multi-scale process that happens on many different scales, from the galaxy scale down to the protostellar scale, and it's extremely inefficient in terms of the amount of mass that can be turned into stars compared to the amount that does get turned into stars is very small. And this happens on the regulation of that process happens on many scales. And I'm mostly going to be, we want to understand how that happens. We believe that mostly on the scales of clouds where most of these stars are born, this regulation is mostly determined by massive stars. But we are still, it's still debated in the literature to what degree certain mechanisms of basically injecting radiation from these massive stars acts to disperse clouds in which these stars are born. So one of those effects should be stellar winds. So this is basically you put the radiation from these stars into the atmospheres, which results in massive outflows. As Eric mentioned, you have velocities of these winds of thousands of kilometers per second. They shock, creating extremely high pressure gas that acts to at least in the classical model, create an overpressured bubble that disperses a cloud. So if we think about stellar winds in the context of this classical Weaver model, they should dominate early feedback processes. However, if we look at observations that have been coming out over the past 20 years or so, they show that in general, this isn't the case. These mostly are observations of the X-rays that you would observe from the hot gas. And these X-ray luminosities are much lower than you would expect for the classical Weaver solution. And in simulations that also include all the different effects that massive stars can have on dispersing their clouds, it is generally seen that winds are not that important of a factor in setting the star formation efficiency. So we're generally seeing that winds are quite weak, but what exactly could be going wrong? So we propose a new theoretical model for the evolution of stellar wind-driven bubbles into turbulent clouds. So to set the context here, we are ignoring the effects of radiative feedback. So just like the Weaver solution, our model assumes expansion into conditions that are characteristic of the clouds in which the stars form, so not into pre-photoionized or heated gas. The classical stellar wind bubble evolution is, I'm basically showing schematically on the left here this is sort of a schematic of the Weaver solution. It has this adiabatically expanding free stellar wind that then goes through a strong shock. This perpendicular shock thermalizes the gas very, very efficiently to very high pressures. And this high pressure gas does work on the surrounding uniform ambient ISM, expanding at velocities that are much greater than the local sound speeds. You have this swept up shocked ISM and then the ambient ISM. And between this shocked stellar wind and the shocked ISM, you have a contact discontinuity. So there's nothing moving across here, which means that there's no wind material mixing by any degree with the ambient material. which means that it's very hard to create intermediate temperature gas other than through conduction. And the surface over which you can create intermediate temperature gas is sort of the spherical surface. So in our solution, this ends up in the Weaver solution, you end up having an energy conserving solution because it's very hard to lose energy when there's no sorts of any mixing. In our solution, we basically have the same interior structure, except now the wind is expanding into a turbulent gas. And because that the gas is turbulent, you end up you have the same sort of shock structure, but now instead of having the shocked ISM with a contact discontinuity, you have a turbulent cooling mixing layer, and then the turbulent ISM in the background. And the proposal of our model is essentially what happens if you are so efficient at removing energy that the solution becomes energy conserving rather than momentum conserving. What happens with that? So I thought I would just show this. Mike Grudick gave this characterization of the differences between these two models on Twitter, and I really liked the simplification of this very complicated work. It really gets across sort of the main points. And then I found a picture of a fractal cow on Google, so I had to show this. The basic difference is the Weaver model is the spherical cow. We use a fractal cow instead, and it turns out that things are very, very different. So what are the consequences that this has for the evolution of the wind bubble? So here I'm showing basically the time it takes to disperse a cloud. The idea here is that you have a central wind source that's a cluster. I'm varying the mass of that cluster by a few orders of magnitude. So from 10 to the 3 to 10 to the 5 solar masses. The cloud is assumed to be a spherical, not really spherical in our solution because it will need to be turbulent, but this is basically just saying what is the difference between a momentum conserving solution and an energy conserving solution. So our momentum conserving solution are the solid lines here, and the Weaver energy conserving solution are the dashed lines. And I'm basically showing what happens if you vary the density of the cloud or its radius, because I'm fixing the mass of the cloud. And the general takeaway is that wind effects are much weaker than in the evolution, the Weaver evolution suggests. And that's what's being shown here is that the time it takes to disperse the cloud is almost an order of magnitude larger in the efficiently cooled solution than it is in the Weaver solution. Here's the same general picture, but with a few more quantities. So the velocity of the shell of gas when the cloud is dispersed is much lower in our solutions. The star formation efficiency required to disperse the cloud, this is a sort of assuming you have a delta function of star formation that's instantaneous in space and time. How big does that star formation need to be in order to disperse the cloud? That is much higher in our solution than in the Weaver solution. And interestingly, for the sort of motivation that I talked about before, the pressure of the hot gas, which is where you get the X-ray luminosity from, is much lower, almost by 2 orders of magnitude in our solution than it is in the Weaver solution. And this is exactly because you are removing so much of the energy through turbulent mixing. So I'm going to get back to the details of the turbulent mixing, but first of all, I thought I'd show some pretty pictures. So in paper, that was sort of the theory paper, and then in this second paper, we validate the theory with a large suite of 3-dimensional hydrodynamic simulations. Here I'm showing a slice through one of the simulations run at high resolution for parameters which are something like a superstar cluster. So this is 10 to the 5 solar masses within a radius of 2.5 parsecs. And the panels are showing density, pressure. This is cooling time versus pressure of the gas, which we predict. One of the predictions of our theory is that the cooling time is inversely proportional to the pressure of the gas. That's sort of what you see here, especially in the in the gas that cools very efficiently. This is the momentum being carried by the bubble, the temperature structure, temperature density phase diagram. This is the fraction of gas in the wind. You can see all of this beautiful mixing structure. And this is the cooling density. We'll get back to that as well. And the temperature histogram weighted by cooling. And we can see what temperature gas is doing most of the cooling. The main thing that I want to get across here is that there's this fractal interface. It's a very, very complicated interface between the hot gas and the surrounding cold medium. We capture the process of wind material being mixed in, and our prediction for the cooling happening mostly at one temperature is, in fact, what pans out within this simulation. But the general thing that I want you to get from this picture is that these bubbles are a mess, and it doesn't seem like any sort of simple prediction would match. It would tell you anything about the evolutions of these bubbles, but that turns out to not be the case. So here I'm showing the evolution of the effective radius of the bubble. So this is sort of the volume equivalent radius of hot gas in our simulations that have a 20 parsec radius clouds. These are sort of the lowest density, largest clouds, something like a giant molecular cloud. And the colors here are corresponding to differences in the star cluster mass. And I'm showing basically the line styles here are corresponding to resolution, but essentially, and the solid lines are the highest resolution. We show that the radius of the bubbles very closely follows what you would expect from the momentum conserving solution, which is pretty much just what is the momentum input rate of the wind, and you have a t to the 1/2 scaling. So that's what's being shown with these black lines. So despite these bubbles being such a mess, the predictions are actually matched quite well. And you also see that in the momentum of the gas. So the radial momentum carried by these bubbles should increase linearly in time in a momentum conserving solution. And that's pretty much exactly what you see. In our theory, we include some fudge factors that account for this not exact match of this theory. And we talk about and explain where that comes from physically. So to set you up for a little bit more math behind the fractal theory, I thought I'd show you this pretty video of the evolution of these bubbles. So here I'm showing one of the 20 parsec clouds. In the upper left, I'm showing density. This is pressure. This is the cooling density, and this is going to be the fraction of the gas that is in wind material. And hopefully, this plays all right for you, but you can see that we've basically set up these winds in this turbulent background. You can see as we're sort of positing that most of this cooling is going on at this fractal interface structure. There's lots of interesting mixing that goes on here. And the pressures, we can think the pressure scale that would be here for the Weaver solution would be much higher. The pressures are much lower in general. Okay, so to get to some of the math, now that we've had a break with some of the pretty pictures, we want to sort of say, is it feasible to explain that this energy can actually be lost so efficiently? So one way to think about that is sort of comparing the flux of energy that is being provided to this turbulent mixing surface to sort of the equivalent flux of mixing away that energy. So the flux that's being provided to the surface is essentially the enthalpy of the hot gas times the post-shock wind velocity, sort of how quickly the flux of energy is being provided to this surface. But how do we think about the equivalent flux being mixed away? The potential for cooling from a fractal turbulent boundary layer is kind of complicated. We're probably thinking about the same enthalpy flux. It's this that's sort of the energy density that's being cooled, but you want to think about a different velocity scale that is being compared against. So we want to seek sort of this characteristic velocity scale for absorbing hot gas energy. This basically depends on the velocity scale at the scale where most of the cooling is going on. So that can be accounted for by basically the velocity scale in the outer energy containing scale. This is sort of characterizing the turbulence overall. You then want to account for the fact that the actual velocity that matters is on the cooling length. So that's what this term is accounting for. It basically depends on the fractal structure, but also the shape of the structure function of the turbulence. And it acts to enhance the amount of cooling that can go on. And finally, the flux that's being provided from this wind is sort of spherically expanding, but the area over which you can mix away this gas is much more complicated than that. It has this large fractal structure, which means that you basically have an enhancement from the fractal structure because there's more area over which you can mix things away. So that's what this term is accounting for. I see that I have not much more time, but I will try and go quickly. So the basic idea that we want to get across is that we can measure these things. The two things that this basically depends on are the velocity scale in the turbulence and the fractal structure. And we can measure that in our simulations and basically compare this term to the post-shock velocity of the wind to see whether it actually makes sense. It's self-consistent that we're mixing away as much energy as we should be. So we measure the fractal dimension of these bubbles, basically using the scaling of the isotemperature surfaces of these bubbles. So basically, we select gas that is at 10 to the 5 Kelvin, which is basically which tracks this interface. And we measure the area of that surface on different scales and look at the logarithmic derivative of that area with respect to the scale on which you measure it. And that gives you this excess fractal dimension. We note that the stronger winds have less fractal bubbles. We talk about that as well, but I don't have too much time to go into it. This should go to 0 at the resolution scale because you're not forming any smaller structure when you get to the resolution scale. But generally, d equals a half is about a good number to use in these cases. So we can also measure the turbulent spectra function that basically gives us the velocity level at the energy containing scale and also the shape of the structure function overall. And I'm also, so this is I'm showing for the 20 parsec cloud, 10, 5, and 2.5. These are the different sizes of clouds that we're showing. The velocity scale itself doesn't change that much with the strength of the wind. So I'm varying the strength of the wind by 2 orders of magnitude, but the velocity only changes by a factor of 2. So this is probably linked to the structure of the inner shock. Don't have time to go into that, unfortunately. But basically, we measure the structure function as well as the fractal dimension of the gas, and we can use that to show that basically this effective inflow velocity that I'm getting from this term essentially is we can use that to compare that to the post-shock velocity of the gas, and we see that in almost all cases this effective velocity at which you're able to take hot gas to cool away energy out of the hot gas is larger than the velocity at which hot gas is being provided to this surface. So it actually makes sense. It's self-consistent that we are removing as much energy as we think we should be. So I guess with that, I'm maybe 3 minutes over time. I will say that wind effects are much weaker than we thought. It is still true. I don't mean this to say that winds are completely unimportant. They can still dominate at early times, and we derive some characteristic time scale or sort of spatial scale for when that should happen. And at these earliest time, the photoionized gas should be sort of feedback from photoionized gas should be subdominant. And this is important for your most extreme star formations. And with that, I guess I will take care.
Thank you. So do we have any questions? I'm not seeing any at the moment. I do have a quick question, which is, I see Guillermo's got his hand up, but I've started, so I'll finish. So have you, your models presumably produce some outputs that you can test on real data. So have you done any of that? Do your models fall kind of closer to reality than these earlier Weaver models do?
Yeah, so we have, you can, for example, you can put estimated hot gas pressures onto this plot as a function of from sort of the LMC or the SMC, for example. And they generally lie, and that you can get those numbers from a few different papers, like Olivier et al. 2020 was the most recent one. But it is a bit of a hard measurement, but those points generally lie way below where the Weaver solution would predict that they should be. At the same time, so we've done sort of a schematic comparison. In order to do the real apples to apples comparison, I think that these wind models need to be included in a slightly more realistic star formation scenario where you're including radiation effects, because that sort of changes the thing that you're mixing into, and it can change a lot of the results, we think.
Yeah. Okay. Cool. Thank you. I do see a hand up from Guillermo.
Yeah, so I wanted to ask, I had two questions really. One regards cloud lifetimes. In this dissipation time plot that you showed, it seemed like the dissipation times from the original Weaver model were very short. And which would imply that just winds alone would produce clouds that are very extremely short-lived, right? Even without any other source of feedback or turbulence. So that doesn't seem so I wonder, like, where do current estimates of cloud lifetimes fall within this, and what makes this kind of how does that compare with this new model that you have? And the other question I have is regarding the pressure structure that you see in your simulations. Most photoionization models that we kind of dumb observers use, assume isobaric conditions. So your simulations don't look isobaric at all. So if you could comment on the impact that would have on kind of simple photoionization models.
Yeah. So first of all, on your first question, you're right that the Weaver this dispersion time given by the dispersal time given by the Weaver solution is very, very small. Some people have used that model to basically say, well, that means that because we use the Weaver model compared to sort of typical timescales for clouds to say, well, winds must be the most dominant form of feedback because they are the thing that can act over such short timescales, and we're saying sort of that isn't realistic. It's a little bit hard to compare these numbers to sort of the cloud dispersal timescales that you get from observations, because those are thinking about sort of extended star formation, and this is sort of if you just have a point source of star formation in time and space. But the cloud dispersal timescales is generally, I would say, a few million years. So this is much closer to that, and you would generally expect that these timescales to get longer when you consider extended star formation. As for the pressure structure, it is actually reasonably, there is a plot in the second paper. There is a plot in the second paper that where we show the evolution of the pressure over time. As you say, it's not, you know, completely isobaric, but it is reasonably isobaric. Compared to the, I guess it can vary by a factor of, I believe it's 4, but I'd have to look at the.
Okay, that's not so bad.
Yeah, it's not terrible. Yeah.
Okay.
Within the hot gas, I mean. So it's sort of this stuff is reasonably isobaric.
That's like the 10 to the 4 Kelvin gas or the 10 to the 5, 6 Kelvin?
This is the 10 to the 6, 7, yeah, Kelvin gas.
Okay, sure. Yeah, I guess what I was asking is, you know, I think models like, I don't know if you're familiar with things like the warp field models that the Klesen group is producing in Heidelberg, where they are like simple. I mean, they're not simple, but they're the equivalent to like a static cloudy model, but include dynamical evolution of the star forming region and the development of a wind bubble and a shock layer and, you know, the expanding ionization front, etc. So, and then they basically post-process that, you know, with Polaris, you know, and Cloudy to predict, you know, what it would look in emission lines, for example. And I think an assumption there is this kind of isobaric, you know, assumption from all these phases. So, but basically what I see in your plot here is that from this, you know, 10 to the 6, you know, Kelvin gas, 10 to the 6, 10 to the 7 Kelvin gas that is dominated by the wind, that is like 10 to the 5, 10 to the 6 in pressure here. You know, there's like a drop of like an order or 2 orders of magnitude once you go to the 10 to the 4 Kelvin gas.
Well, it's
which
a little
is
bit
actually
hard.
what produces, yeah. But
yeah, I was going to say it's hard to separate exactly what the differences are in this simulation because it's such a sharp contrast, as you're saying. The thing that I would point to is sort of these mixing layer simulations that a lot of this work is sort of predicated on, which show that generally you'll get dips in pressure when you look at lower resolution models, but that's mostly a numerical effect. And that across the mixing layer, it is actually a pretty good approximation to consider that it is isobaric. And that stuff isn't being completely well resolved within these simulations, but the sort of higher resolution, smaller scale simulations show that.
Thanks.
I'll also just comment that, you know, the warp field is 1-dimensional. This is 3-dimensional, and the so these simulations don't have photoionization, but Lachlan has done some preliminary simulations that do include the photoionization using Jong-Gyu Kim's ray tracing and radiation. And there, the pressure is quite similar in the photoionized gas and the hot gas.
I see. That makes sense. Thanks.
Okay, I think we'll have to stop there for today since we're now past the hour. So thanks again to both of our speakers, Eric and Lachlan, and we'll be back here again in a couple of weeks for another couple of talks. So thanks all for coming along, and see you all in a couple of weeks.